In the last lessons, you learned how to add and subtract matrices, as well as how to multiply a matrix by a scalar. In this lesson, you're going to learn how to multiply two matrices together. So here's our first example, where we have matrix A and matrix B. And when we multiply A times B, the way that we can represent this is by putting the A next to the B. So A next to the B means A times B, where we have 0, -1, 3, -4, and then the other matrix, -4, -3. Now, in order for matrix multiplication to work, the dimensions need to be very specific. So the dimensions of the first matrix is 2 by 2. The second matrix, you have 2 by 1, 2 rows and 1 column. And in order for this to work, the middle numbers here, so the 2's, if you put them next to each other, the 2's need to be the same. So if it's not both 2's or both the same number, then you cannot multiply together. And then the resulting matrix, after you multiply, will be these last two numbers out here, the 2 by 1. Okay, so this one does work because we have the same number of columns in the first matrix as the number of rows in the second matrix. Now when you multiply, there's kind of a weird process where what we do is we're going to take this first row and multiply it by this first column. And you're going to take the first element of the first row, multiply it by the first element of the first column, and the second element of the first row, multiply it by the second element of the first column. So what I have is going to be 0 times -4, and then -1 times -3. And then we add those together, and we're going to get 3. Now that 3 is going to go right here. We said the resulting matrix will be 2 by 1, so we have 2 rows, 1 column. We were multiplying the first row by the first column, so the answer we get after we multiply and add is going to go in the first row and first column of the resulting matrix. And then you repeat and you multiply the second row of the first matrix by the column of the second matrix. So when you multiply, same thing, you're multiplying the first elements of the row and column by the second elements of the row and column. So -4 times 3 plus -4 times a -3 will give you a -12 plus a +12, which would equal 0. And that 0 is going to go in the second row, first column, because we were multiplying the second row by the first column. So the 0 is going to go right there. So my solution, my resulting matrix, would be this matrix right here, the 3 and 0. Here in the next example, we're using the same matrices, but instead we're going to take B times A. And so the first matrix is 2 rows by 1 column. The second matrix has 2 rows and 2 columns. So when you put it next to each other like this, 2 by 1 and the 2 by 2, we check to make sure that we can actually multiply. And to check, we look at these numbers right here on the inside, this 1 and the 2. In order to be able to multiply, these numbers need to be the same. In this case, they are not the same, so therefore we cannot multiply these two matrices. Example 3, here we have these two matrices that are multiplying together. Now this time we have more than one column in the second matrix. But it's the same concept that we use for example 1. So the dimensions of the first matrix are 2 by 3, the second matrix is 3 by 2, and because these numbers are the same, then we can actually multiply. And the resulting matrix would be the dimensions of 2 by 2, those two numbers in yellow. So when I multiply, same concept with example 1, where I take the first row of the first matrix, multiply it by this first column of the second matrix. And I'm going to multiply the corresponding elements, where element 1 multiplies with element 1 of the second matrix, element 2 multiplies with element 2, then element 3 multiplies with element 3. So I multiply and add those all together. So when I do that, I have 2 plus a positive 3, which is 5, plus a negative 9, which is negative 4. Now the resulting matrix is 2 by 2, so it's a square matrix, and the negative 4 goes in the top left corner because I'm taking the first row, multiplying it by the first column. So it's going to go in the first row, first column of the resulting matrix. And now I repeat again, multiply this time the second row, the first row by the second column. So the same thing, except we're going to do it with the second column instead. So now we take 2 times 2, the negative 2 times negative 1, and the 5 times 3. Those are the first elements multiplied together, the second elements, and the third elements. So when I multiply and add them together, what I get is going to be 21. And because I multiplied the first row by the second column, my solution, the 21, goes in the first row, second column of the resulting matrix. Now I need to figure out these other two numbers down here. So looking at the same problem, we have the same dimensions, and now we're going to multiply the second row by the first and second column. So same thing again, you multiply the corresponding elements. So element 1s we're going to multiply, the element 2s we're going to multiply, and the third elements we multiply. So you multiply and add them together, and when you do that, you're going to get 10. So 10 is going to be in the second row, first column of the resulting matrix, which is going to be right there. And then I repeat one last time, now with the second column and the second row. So same concept, I'm going to multiply the element 1s together, element 2s, and the third elements. When I multiply and add them together, I get 8 plus 4 plus 0, which gives me 12. So 12 will go in the bottom right corner because I'm multiplying the second row by the second column. The resulting number goes in the second row, second column of the resulting matrix. So that is how you multiply two matrices together. And we can have any number of dimensions for either matrix as long as the number of columns in the first matrix are the same number of rows in the second matrix. Now a few properties that we need to discuss with multiplying matrices, and the first one is the associative property. And this is the same property that we had for matrix addition as well as for scalar multiplication, where we can group together different things in parentheses. So when you're multiplying three matrices together, I can multiply the first two matrices together and then multiply the third, or multiply the last two together and then multiply the first after. So here we have three matrices. And if I were to multiply the first two, so A times B first, and then multiply the third one after, what I would get would be found by taking this column right here, the 2 and the 4, multiply it by the first row, so 2 times the 1 plus 4 times the 2, which would give me a 10. So 2 plus 8 gives me 10. Then 2 times negative 1 and 4 times 3 for the second number, which would also give me 10. And then I multiply these two matrices together, 10 and 3, negative 2 and 5. And this one, you have the original matrix. For the first one is a 2 by 1 matrix. The second matrix is a 1 by 3 matrix. So we can multiply because these two are the same, and the resulting matrix would be a 2 by 3. So it's a 2 by 3 matrix, and I take this first row, or first column, multiply it by the first row here, which is just the two numbers 3 and 10, which gives me a 30. Same thing with negative 2, multiply it by this first row, so the first row by the second column, we have 10 times negative 2 to get negative 20. 5 times 10 gives me 50, and then do the same thing again for the second row right here. Second row by the first column would give me 10 times 3, which is 30. Second row by the second column gives me 10 times negative 2, or negative 20. And then 10 times 5 would give me 50. So my resulting matrix would be right here. And then if you were to do it the other way, where you multiply b times c first and then multiply by a. So looking over here, we have the 2, 4, 3, negative 2, and 5. You multiply the first column by the first row. So we have 3 times 2 would give me 6. And then second column by the first row, we have negative 2 times 2 to get negative 4. And then third column by the first row, we have 2 times 5, which is 10. And then repeat now for the second row. 3 times 4 is 12, and then negative 2 times 4 is negative 8. 5 times 4 would give me 20. So now I can multiply these two matrices together, where this one's 2 by 2, and the other one is a 2 by 3. So these are the same. I can multiply, and the resulting matrix would be the 2 by the 3. So when I multiply, I take this first row, multiply it by the first column, 6 and the 12. So I take 1 times 6 and then 2 times 12, add those, and that's going to give me 30. I take the second row times the first column, so 1 and 2. I take 1 times negative 4 and 2 times negative 8, add those together to get negative 20. Repeat again for this third column in the first row. I take 1 times the 10 and 2 times 20. 1 times 10 is 10, 2 plus 20 is 40. So add those together and you get 50. Now repeat one more time with the second row. So second row times first column, I get negative 1 times 6, which is negative 6, plus 12 times 3 is 36. Add those, you get 30. Same thing with the second column. Negative 4 times negative 1 plus negative 8 times 3 gives me positive 4 minus 24, which is negative 20. And then repeat one last time with the third column. Third column times the second row. We have negative 1 times 10 plus 3 times 20. You add those together and you get 50. So long story short, this solution will be the same if I were to multiply a times b first or multiply b times c first. Then we have the distributive property, which says that I can multiply a times b and then add a times c after the fact. And I will leave this up to you to prove to be true, but you will find that when you multiply matrices together, the distributive property will still apply. Next we have the identity matrix for multiplication. And now we learned that the identity matrix is a matrix that you can add, subtract, or multiply, or whatever operation we're doing, such that the original matrix does not change. And now in this context we are dealing with matrix multiplication. So an identity matrix for multiplication is a matrix that can be multiplied without changing the original matrix. Now for this to work, the identity matrix must be a square matrix. And the main diagonal from upper left to lower right must have all elements of 1, while all the other elements are 0. So for example, the identity matrix for a 2 by 2 matrix, this main diagonal would be a 1, all 1s, and everything else would be 0s. For a 3 by 3 matrix, this main diagonal from top left to bottom right are all 1s, and everything else are 0s. For a 4 by 4, we have this main diagonal is all 1s, and everything else is 0s. For a 5 by 5, same thing. This main diagonal is going to be all 1s, and everything else are all 0s. Now let's prove that the identity property actually works. So here we have two matrices multiplied together, where the second matrix is your identity matrix. Now when you multiply, we see that we have a 2 by 2 matrix multiplied with another 2 by 2 matrix. So we can multiply because these two middle numbers are the same, and the resulting matrix would be over here in the yellow. So the resulting matrix would be also 2 by 2. When you multiply, you take this first row, multiply by the first column, and you multiply the 1 and the 0, and the negative 1 and the 0, and you add them together to get 0. And now when you do the first row and the second column, we get 0 times 0 plus negative 1 times 1 which will add to give me -1. And that goes in the top right corner. And now with the last two, we take the second row by the first column. So we have 3 times 1 plus -4 times 0, which would give me a 3. And that's going to go in the bottom left corner. And then we do the second row by the second column. So we get 3 times 0 plus -4 times 1 to get -4. And that goes in the bottom right corner. And notice my resulting matrix is exactly what I started with. I started with 0, -1, 3, -4, and I ended up with 0, -1, 3, -4. So when you multiply by the identity matrix, the original matrix does not change. And we also have what is called the multiplicative property, which says that if I multiply a matrix by the 0 matrix, then my resulting matrix will be also the 0 matrix. So to recap all the properties that we have for matrix multiplication, we have the associative property, we have the distributive property, the identity property, as well as the multiplicative property. And that concludes our lesson for today. We will see you next time.